later on, we'll have you log into a virtual machine running on Amazon Web Services, and to know which machine you're going to log into, you're going to use your row number in this roster page. You also are probably going to want to watch the slides on your own laptop. You might want to cut and paste the commands later on during the hands-on, and so the second link should take you to the slide deck. I think I'll wait till about 2 minutes after and say that again. So I'm going to wait a couple more minutes and then kind of just repeat what I just said and get started. Yep, I'm good. Thank you. So again, we're gonna have some hands-on exercises, probably about halfway, 2/3 the way into this tutorial. And if you want to participate in that part, you need to go to this first URL and put your name in the spreadsheet and make a record of the row number in that spreadsheet, because you're going to use that to determine which VM to log into. I think we'll wait one more minute. So my name is Steve Wallace, and I'm the acting executive director of something called InCenter. InCenter is located at Indiana University, and we do education in translational research and networking, focusing mostly on software-defined networking. Chris Small is one of the researchers with InCenter, and Chris set up some of the virtual technology that we're going to use to walk through the tutorial. Ask questions at any time. Probably the more questions, the better. This workshop usually is a full-day workshop, and so I've kind of hacked at it to make something that's going to fit 90 minutes, and I've not done it in this format before in this time period. So for those of you who have just walked in, part of the tutorial will be hands-on, and if you would like to participate in that, you should go to the URL on the screen and it'll take you to a Google Docs spreadsheet. Put your name and email address. If you want to be anonymous, you can put a fake name and email address, but it's important that you put something in there so that you have a row number, and you remember that row number as you'll use that row number to select the VM that you're going to log into for the hands-on exercises. Okay, we'll go ahead and get started. Anybody trying to get on the roster spreadsheet and isn't able to, for those walking in, we're going to do some hands-on exercises during part of this tutorial. If you want to participate, you need to log into this, the first URL on the screen, which is just tinyurl.com/nanog57-roster. And besides collecting marketing information from you, the purpose of that spreadsheet is to assign you a unique number so we can tell you which VM to log into. Okay, we're calling this OpenFlow 90 minutes. We'll see if that works. Again, I'm the acting executive director of something called InCenter at Indiana University, and the easiest way to explain InCenter is I call it the research arm of the global NOC, which is located at IU. There is a demo of OpenFlow software and hardware next door. I think that's going on most of the day today and tomorrow. There are hours posted on the sheet, but you can go in there and actually see this stuff working. Indiana University has developed a service that runs on a nationwide research network called Internet2. It's a production service. And they have a really cool orange box over there that actually goes to the Arctic with computer gear in it normally, and we borrowed it for this trip. We got some more people coming in. I'm just gonna, I'll do this this will be the last time. We're gonna have some hands-on component of this later, and if you wanna participate in that, please go to the URL at the top of the screen, just tinyurl.com, nanog57-roster. You'll need to know what row your name is associated with in the spreadsheet to select the correct VM to log into. And more people are coming in. Tell you what, we'll come back to this slide right before we start the hands-on stuff. Again, my name's Steve Wallace. You're welcome to send me email, just ssw@iu. And this is Chris Small. He's chsmall@indiana.edu. A little bit about the tools we'll be using today. When we get to the hands-on exercises, we're going to use Amazon Web Services. We're going to fire up VM instances in their EC2 service. We've created an Amazon machine image that contains all the stuff you might want to play with if you're going to play around with OpenFlow, and we've made it public. So after this tutorial, should you want to play some more with the same tools, you should be able to do that pretty easily. For those of you not familiar with Amazon Web Services, you can create an account on AWS and get a fair number of hours. I forget how many hours, but hundreds of hours free on their micro instances when you first get your account. So you'd be able to set this up and use these tools for free. Another tool that we're going to be using is something called OpenVSwitch. So OpenVSwitch is one of the items on the Amazon machine image that we'll be using today. OpenVSwitch, among other things, can act as an OpenFlow switch, and it also comes with some utilities to make that are good at debugging OpenFlow switches, and it also has a component that can act as an OpenFlow controller. We're going to be using a network sniffer called Wireshark. Many of you are probably familiar with Wireshark. I believe it's the case that the default distribution of Wireshark does not include the OpenFlow dissector. And so you have to build a special version, and the Amazon machine image that we'll be using has that version of Wireshark. And we're going to be using something called Mininet, which is an open source virtual network tool. You can essentially design networks with arbitrary topology on your laptop. And it can, the switching components in those networks can be under OpenFlow control. So you can play around with a network of any kind of topology, and it supports OpenFlow. And in fact, I mentioned earlier next door, they're demoing some software that's used in a production network to provide essentially circuits on demand or bandwidth on demand using OpenFlow. And when they develop that software, they use Mininet as their test environment. So one of the difficulties with explaining OpenFlow is it's sort of like talking about HTML and trying to get across to folks early in the day that, HTML actually will change our entire life. But we're going to start with these tiny components, these just tags. So OpenFlow itself is pretty simple. It's pretty basic, but I think it has potential to change the way we do networking. Certainly software-defined networking does, and OpenFlow is an interesting example of that. We're going to talk today mostly about the sort of the low-level stuff, and we're not going to really show any polished OpenFlow applications, but we'll talk about some innovative uses of OpenFlow. Okay, some logistics here. If you want to do some of the hands-on exercises, participate in the hands-on exercises later in today's session, you need to go to this tiny URL and put your name in a spreadsheet. How many people do we have? So about 27 of you have done that so far. And you'll be using the row number on that spreadsheet to connect to some virtual machines running on Amazon Web Services to do the exercises. And although we'll do that a little bit later when we want to go ahead and get you started down that direction. So if you want to fully participate in the hands-on part, and the hands-on part will be useful even if you're not doing it hands-on. We'll be talking through most of it. But if you want to do it, you're going to go ahead and want to open up 2 terminal sessions, and you should open up those terminal sessions username OpenFlow at VM and X gets replaced with the row number in that spreadsheet. So don't pick a random X, actually use the row number in the spreadsheet. So SSH, OpenFlow at VM, whatever the row number is in the spreadsheet, .training.incenter, which is spelled awkwardly, INCNTRE.org. And the password is OpenFlow. You can also point your browser. You'll need to also do this. So you're going to do 2 terminal sessions, and then we used to have folks use an X server on their laptop to work with Wireshark, but apparently most people have just gotten over X, and when we have a class, it's too difficult to work through getting X installed for everybody. So we have Wireshark available via something called Guacamole. So if you point your web browser to VM X being the number again from that row number in the spreadsheet, .training.incenter spelled that weird way, .org, port 8090/guacamole, you should get an HTML5 rendering of an Ubuntu desktop running Wireshark. And we'll get to the problem you're going to have with this in more detail later, but Wireshark, when it's run in this configuration, spits up an error dialog box, and you have to find that dialog box on the screen and dismiss it before you can use it. So I'm going to leave this up here for just a few more seconds so people can get it. The salient point is you need to go to the roster spreadsheet, tiny URL NANOG 57-roster, sign in, put your name, email. You can put a fake name and fake email if you want to remain anonymous. But that's going to get you a unique row number, and you're going to use that row number to determine what VM you log into and where you point your web browser. How many people are going to do the hands-on stuff? Okay, is anybody having problems getting to the Google Doc or SSHing in? When you go to the registration page, when you go to the registration spreadsheet, one purpose of putting your name in the spreadsheet is to reserve a number, and the number is the row in which you put your name. So if you look to the left of the spreadsheet, there'll be a number. The first one will be 2, because the headings take up 1 and so forth. Okay, so I'm going to I'm going to go to the next page. Okay, normally when we give this talk, it's a full day talk and we go into a lot of detail. And please stop me if things are not making sense, because we've really stripped this down and we haven't tested it. I guess you're our test. What is OpenFlow? So OpenFlow is both a protocol and an API for controlling the forwarding behavior of Ethernet switches in something called the software-defined network. Now, you can have software-defined networks that have nothing to do with OpenFlow. But OpenFlow is a nice open standard that we can use to talk about a specific kind of software-defined network. And that's what we'll be doing today. OpenFlow initially was released by the Clean Slate program at Stanford University. It came out of some security work. Basically, some PhD students wanted to design a network that by default had no connectivity. So today, we connect to the wireless network here and you've got global connectivity. Well, you could imagine certain agencies of the federal government would be interested in a network where you connected and you could get to nothing without making a request, being authenticated, and that request being authorized. And then the network itself actually setting up connectivity to just what you're requesting and what you're authorized for. And so they wanted to do this on a pretty granular network control plane scale. And so essentially they want to be able to do this per TCP flow. And so they needed some way of signaling to the network how to forward things as small as individual TCP flows. And what came out of that was this OpenFlow thing. So that's kind of where it got started. So initially, Stanford released the protocol, and okay. Did I do something wrong? Okay. Sort of like the Super Bowl. Only not for 30 minutes. So initially Stanford released the OpenFlow spec, but then industry got real interested, and industry sort of spun up this thing called the Open Networking Forum. Excuse me, the Open Networking Foundation. I should not say forum. The Open Networking Foundation is kind of a new kind of standards body. It has board of directors, and on the board are companies like Google, Microsoft, Goldman Sachs, Deutsche Telekom, Verizon. Interesting, none of those companies make hardware, or at least make hardware that they would actually sell. They're very much interested in this standard taking off, so there is an ecosystem, I'll overuse that word like everyone, an ecosystem of products and services that conform to that spec, because they need to be able to use that stuff. And so then the more folks that are making equipment that supports that spec and truly interoperate, the better the Verizons of the world can take over the world and offer all sorts of communications. I'm sorry if there are any Verizon people in the room. I don't mean that badly. Most of the material we're going to talk about today is based on OpenFlow 1.0. 1.0 is kind of an interesting version of the spec. It's the first version of the spec that you could get software and hardware that claim to conform to it. It's fairly limited, but being limited, vendors were able to take existing equipment and kind of upgrade firmware and be able to do some OpenFlow 1.0 kinds of things. OpenFlow has evolved quite a bit in the last year, and we're now up to OpenFlow 1.3, which is way different than 1.0. And there was a big jump at 1.1, and we'll talk about that in a bit. Couple more things that are important to point out. So the Open Networking Foundation is not like the IEEE, it's not like the ITU, it's not like the ITF. So it's currently they have, I think, 90 members. Members pay 30 grand a year to be a member of the ONF. Those members agree that if they contribute intellectual property, if they help contribute additions to the specification that require intellectual property that they own to implement efficiently, that they'll share it under reasonable terms with the other members of the ONF. They also are, those 90 members are the folks that are working in the working groups to expand the specification. So not quite as open, but the board members have an interest in making this happen. And there was a, is anybody here from Google? So you can correct me if I say something wrong. I think it was so there's a meeting called the Open Networking Summit, and the last one I attended, there were 900 people there, and the one previous to that, I think there were 300. So this is a rapidly growing group of folks. And Google did one of the plenaries, and they talked about their transition to OpenFlow. So Google has basically two networks. They have their network that faces the public that we use when we type google.com. And then they have the network that interconnects their data centers. They have a dozen or more data centers throughout the world. And they started on a project to convert the control of the devices that switch data among the data centers to OpenFlow. And they're at this meeting saying that we've done it, not that we're planning to do it, not that we're in the process of converting that network to OpenFlow, but that we have already done it. So the network that carries more traffic, the network that carries all the flows among those data centers, the forwarding of the packets is determined by OpenFlow capable switches. They also showed a picture of the switch they built, which I found fascinating because, you've been reading the trade press and, somebody finds a little Google switch in Kansas and it gets all kinds of press. Everybody's curious about what they're really building, and they're pretty tight-lipped about it. Some analysts figured out a few years ago that there were more ports being made than being shipped by the known switch manufacturers. So it's pretty clear that people like Google were building switches in large numbers of them because there was this missing port problem. So during this presentation, Google shows a picture of the switch. And, it's a big, it has a lot of ports on it, switch they built. And during the Q&A, a guy comes up from the audience and says, "Can you tell us more about your switch?" And Google says, "There's nothing really special about the switch, and we don't want to make any more of them." And there were a lot of vendors in the room. And I almost felt that was a setup. I mean, I think Google was signaling, we've moved our entire network, at least the inner data center network, to OpenFlow. We had to build our own switches, but we don't want to keep doing that. Hint, hint. So that, so this stuff is real. It's certainly real in the data center. Okay, so let's talk a little bit about today. Today we typically buy these appliances, and an Ethernet switch would be a simple example of an appliance, but we buy routers and firewalls and all these things. They typically come in the form of an appliance, and they have a high-speed data plane where there's some specialized hardware that makes that's able to forward packets at high speed. And then there's sort of a control plane that provides the features that sit upon that. And typically, the interaction between the data plane and the control plane is that the data plane hardware is table-driven, and the control plane populates those tables. So the data plane usually has hardware features like cams or TCAMs, and then the control plane will populate the memory that drives the behavior of those TCAMs and network processors. And when you buy a Cisco or an HP or whatever or a Brocade, the features you get are usually implemented in this embedded operating system that's part of the control plane, that's part of the appliance. And that is, in some ways, much of the value that you're getting from a particular vendor is the set of features, the reliability of those features, and so forth that sits in that embedded operating system in the appliance. In a software-defined network model, you separate out the control plane from the data plane. And the data plane continues to look very similar. It has this high-speed hardware. But if that's a table-driven data plane, the formation and the maintenance of that table, instead of being done by software that's running on the appliance, like the switch, is actually outside of the device. And we call that a controller. In OpenFlow parlance, we call that the OpenFlow controller. So you have a protocol that the OpenFlow controller uses to manage this table in the high-speed forwarding device. And you also have an abstraction of that table and an API for manipulating that abstraction. And so basically you develop software running on this controller to implement the features of the switch. And this has a lot of advantages, and it's different, and there are probably some downsides. But now I have a regular server running an operating system and able to easily throw lots of CPU cores and memory and have developers work in a well-understood environment to develop those features. So I can write code on my Linux box that is going to implement features in my network, even features that require very high speed. Because the control is centralized, it can be coordinated better. When Google talked about the advantages to switching to this model for their inter-data center network, the specific advantages that they were seeing immediately were two. One is they described their ability to more easily simulate and understand what happens under different failure scenarios. So you've got a bunch of boxes talking different routing protocols, and a link fails or box fails. These are all distributed systems that are healing. And understanding what their state will be under any particular failure condition is somewhat fuzzy, depending on how complicated it is. You have timing issues, and they're all acting as autonomous systems, trying to understand what the network looks like and how they should behave in this new configuration. So Google said one of the nice things was, if you have central control, that problem is easier to solve. That you are centrally forcing the behavior of all these distributed devices. They're not communicating back and forth to each other and doing it autonomously. So understanding what things will happen for any particular failure is much easier. This led them to be able to run links at higher utilization. So what they said was, now that we've better understood how things will fail, we're able to run our links at higher levels of utilization because we have a higher degree of certainty in understanding what will happen when any particular failure takes place. So there's this advantage of having sort of this central control over your network domain in that you have the full view right there. It's consistent. Now, yeah, it may vary between that central view and what's really happening in all your devices, but you have this view that's self-consistent. It's central. You're developing features on a real operating system with normal software developer tools, and that puts you in a different place. It enables you to adapt more quickly to adding features, and it gives you some other advantages as well. It doesn't come without some pain. And when somebody says, what is software-defined networking? The core of software-defined networking is the separation of the control and data plane and the centralization of, yeah? Great question. So the question was, if you are doing the features in the controller, that how do you get the line rate out of the device? And if you think about it, today, when we look at these appliances, you have this embedded operating system and control plane that can't do anything at line rate. And basically that control plane is setting up tables, whether they're fibs and routers or whether they're forwarding tables with ACLs and TCAMs as a part of layer 2 equipment. That control plane is basically maintaining those tables, and then the high-speed hardware is using what's in those tables to determine how to do things at line rate. And so what you're moving off of the appliance is the maintenance of the tables, not the high-speed forwarding capability. Now, there are corner cases where things don't work well, but and I'll show some more specific examples of that. So again, in a software-defined network, and OpenFlow network specifically, you have this centralized device, the controller, and you might think of the features and the value add as being there rather than in the switches. And you could think, well, that might be kind of disruptive for some of the companies I deal with. You might, for example, buy a particular controller based on the set of features it supports and have some flexibility in which switches you buy as long as they have enough capability to work with that controller. The way this appears to be working out is there are incumbents, hardware manufacturers that are making their own controllers, they're making their own OpenFlow controllers, and the software companies making their own, startup software companies. Nicira was one that was purchased by VMware for $1.2 billion not too long ago. There's another startup called Big Switch. And these folks are just making the controllers. So they're making features for networks, but they're not actually making any hardware. They're just making the software. And the controller, you can think of it as sort of your network operating system. And it's running on top of Linux probably, but you think of the controller as a network operating system, and it has some built-in features. The controller manufacturer has put a bunch of features in that will compel you to buy their controller. But in addition to that, they have, it's a platform for applications to be developed upon. So you have the controller, the controller vendor's features, and then they're exposing an API that can run applications written by third parties or maybe the customer. Maybe you have a particular thing that you need to do to comply with lawful intercept or some legacy bridge stuff that you need to do, and you write an application that runs on the Big Switch controller. Or maybe there's a company that specializes in payment card industry security compliance, and maybe they write an application that runs with the Big Switch controller. And so you start to have this application platform, the network operating system, and a programmable network, and it can change the way you look about how you would address features. There's a new buzz about network function virtualization. Why don't you take this to another step and be able to put network functions in these devices, like firewalls and WAN accelerators and that kind of thing. And OpenFlow can be used in a way that supports that kind of evolution as well by enabling you to finely tune where things go in the network and do that from a central location. Okay, so one of the more important abstractions in an OpenFlow environment is something called the flow table. Now, unfortunately, it did. try plugging this in, unplugging it. Okay, for those of you who have the slides up, and I'll try to be very descriptive, one of the most important abstractions for OpenFlow is the flow table. And unfortunately, the OpenFlow spec, the 1.0 spec, labels some of the items in the flow table differently than the 1.1 spec. So you have this flow table. It's basically a two-dimensional table, and you have columns, and one of the columns it's called header fields. And these are things that are used to identify a network packet that you want to affect. So for example, it's a tiny URL / NANOG 57 lowercase dash slides. And we okay, so this important two-dimensional thing, it's called the flow table. At a high level, what's going on is you're using the OpenFlow protocol to maintain what's in this table. Excellent. So this is the flow table, and there's more stuff in the flow table than I have up here, but just to start off with, there are these things called header fields. And what could be in the header field section of the flow table? It could be things like ingress port. What port did the packet come in on? Could be Ethernet source or destination address. Could be the Ethernet type field, VLAN ID, things like the IP address, the IP protocol field, and so forth. So you're using things in the header field to identify packets that you want to do some action to over here. Now, this is how most switches are made today. It may not be exactly like this, but it's close. There's some TCAM table in a layer 2 switch, or there's a FID in a layer 3 device, and it's using some table that some embedded software is maintaining to do the high-speed stuff. And we're just, in the OpenFlow software-defined networking stuff, we're just taking that embedded software and moving it outside to a central box. So basically, with this kind of table controlling the actions, we can do things. Oh, let me go back here. And then once you identify a packet as one you want to do something to, there are actions that you can do to that packet. And the actions are pretty straightforward. You know, you can forward the packet. And when you forward a packet, you can forward it out all the ports. You can forward it to the controller. That's called a packet in event. You can tell the packet to take the normal path of the device. So some OpenFlow devices can have kind of a split personality where they're running OpenFlow in one context and something else, maybe a firewall in another context. And within OpenFlow, you can say, take this packet outside the OpenFlow context. And you can modify the packet. So some of the actions include modifying the packet. You can essentially modify the same fields that you use as header fields to identify the packet. And then there are a bunch of counters. So here's some more specific examples. So in this make-believe flow table, I might have something that says if the ingress port was 2, if packet came in on port 2, then I want to drop the packet. Simple rule.
I might say if the IP address is 129.79.1.1, maybe I want to rewrite that IP address because I'm doing a network address translation gateway and forward that packet out port 3. I might say if the Ethernet address has a certain value, and by the way, with the IP addresses and Ethernet addresses, you can mask those matching values. I might say if it has a particular value, I want to add a VLAN ID and send that out port 2. I can do things, I can perform more than one action at a time. I can say if the ingress port equals 4, forward that packets out port 5 and 6. So I can have any number of actions. Well, the protocol and the spec allows that. It's implementation dependent as to how much a switch will support. But I can have multiple actions that I can apply to a packet that matches the header fields. And there's also something called priority, which allows the switch to determine the appropriate action when a packet matches more than one flow table entry. So for example, I might have a rule that says if the ether type is R, forward the packet to the controller. And by the way, that literally means that packet gets encapsulated in a TCP stream and sent to the controller, which could be very useful and very dangerous. And I've got another rule down here that says if ingress port equal 2 and the ether type is R, then forward normally as the normal context of the device would do. Now notice if I had a packet that matched the last rule, it would also match the next to last rule, but the action will be applied by the rule with the highest priority, highest number. So in fact, this last one with the priority 40,000 would be what is applied to a packet that came in port 2 and was the Ethernet type part. So I said you could forward to a port, you could forward to multiple ports, and then there are special ports. You can forward to the controller. Again, that's called a packet in. Normal, send packet to the non-OpenFlow function of the device. Flood, do whatever that device thinks is appropriate for flood. And local doesn't get used much. There are also timers in the flow table. So in addition to having header fields and counters and actions and priority, there are timers, and each flow entry can have no timers, which really means timers with 0 value, or they can have an idle timer or a hard timeout timer or both. And this simply says if the OpenFlow controller puts one of these table entries in a switch, it can say this table entry is only going to stay there for so many seconds. Or it's only going to stay there for so many seconds since the last packet actually matched that entry. And the switch itself, not the controller, can remove that entry when either the timers expire. So they're kind of two different ways to think about how you might maintain this table in the OpenFlow switch. And these are not exclusive, but you can have a proactive model. And if you go to the demo in the room next door, they're happy to show you an application where you go to a web page and you essentially draw a point-to-point circuit, and you press a button, and software behind the scenes uses OpenFlow to configure the switches along that path to implement that point-to-point circuit. That's proactive. So before any data flows over that point-to-point circuit, the rules are being put in the switches along the way as to what to do with the data. Reactive is responding to data that's hitting the switch for which there is no rule. So in the default condition under OpenFlow 1.0, and it gets a little more complicated starting with 1.1, but if you send a packet to a port on an OpenFlow switch, and there is no rule that matches
that packet, then that packet will be automatically forwarded to the controller. And in a normal application, the controller will look at that packet, figure out what kind of rule needs to exist in the switch to process that packet. It will update the table in that switch to process that type of packet, and then it will send the packet back to the switch. Now, there's some tricks to make that more efficient. The switch can buffer the packet, and the controller can say, remember the packet in buffer 2, go ahead and reprocess it because I put a rule in that will match on that packet. So proactive is when you put the rules in the switch before the traffic hits the switch, and reactive is when you have the switch sending the controller traffic and the controller is writing new rules in the switch to handle those new flows that are going through. Yes?
So you're sending data traffic to the controller. Isn't that what you said to the
So if you're doing a lot of reactive stuff, one of the things you have to design for is how much traffic would be going to the controller. Generally speaking, reactive is bad, especially in a wide area network. But there are cases where it's not as bad, like in a data center. So in the case of the application that they have across the hallway, it's purely proactive. So no traffic, I believe that's true, no traffic is actually being sent to the controller for the controller to set up a rule in the switch. The controller, based upon a web portal and user demand, is pre-configuring the network for those services. In the hands-on exercises, we're going to actually do proactive and reactive examples, if that works. Okay, normally this is how this normally works. You have an OpenFlow device you're going to put in your network, and you give it some basic information. Maybe you give it its IP address, default gateway, subnet mask, and the address of its OpenFlow controller. Now there's some security stuff too. It can be a TLS connection, so you can have keys and all that stuff. But basically, you take a device, you give it some basic information, you turn it on, and it connects to an OpenFlow controller. The way this is typically designed, especially in a wide area network, is there's some sort of network that exists exclusively for the purpose of supporting this traffic from the switch to the controller. So you plug the switch in, maybe there's a management port, you plug into some management network, switch contacts the controller, and then the controller from that point forward can maintain this table in the switch, which is controlling its behavior. Now, it's not part of the spec, but most OpenFlow devices support kind of an alternate way to talk to them, and you can configure most OpenFlow devices to listen for an OpenFlow connection on a particular TCP port. So you're able to actually connect to them. So something outside, well, some other device can initiate a connection to an OpenFlow device if they have one of these things listening. And they're still talking OpenFlow over this channel. There's no real difference in how the channels work. It's just who initiates them. And many switches support both at the same time, and this can be really useful. Maybe you have a switch that is configured to connect to a controller, and it's part of your network, and that controller implements all these features. But maybe you have a network engineer who's trying to figure out what's going on, and they would like to connect to the switch using OpenFlow and interrogate the switch directly to see what's going on. And so, and we'll do that in some of the examples. We'll actually have a switch that's talking to the controller, but at the same time, you're able to connect to the switch and using some command line utilities, use the OpenFlow protocol to interrogate the switch. Okay, I'm going to give you just a real quick example of how some of this stuff works. Let's say that we're talking about an enterprise. Let's say campus. I come from a university. So let's say a campus, you've got some big OpenFlow network that is all over campus, and you've got a network engineer installing a new device. And they've given this OpenFlow device the basic stuff, its IP address, the address of its default gateway, subnet mask, and most importantly, the address of the OpenFlow controller. And the network engineer, and you know, these are really skilled network engineers that put these devices in the phone closets on campus. They can walk, most of them can drive. They put the switch in the phone closet, they put some wires on it, and they leave. Well, wouldn't it be great if there was some standard way, vendor-independent way to determine how that new thing got wired into the network? What does the topology look like now that this new device is in the OpenFlow network? And this is just an example. This isn't exactly how it's done, but here's an example of how you can do it in an OpenFlow environment, and it gives you some sense of how all this stuff works. So you give the switch its minimum configuration. Switch connects to the controller. The controller will say, you know, what kind of OpenFlow version do you run? How many ports do you have? What kind of ports are they? So forth. And then the controller will put a rule in this new switch. Now, it's also put this rule in every other switch that's connected to it. So all the switches have this rule, but it's going to put a rule in this switch that says if a packet comes in with an ether type of LLDP, send that packet to the controller. So this new device, it puts this one rule in. Then the controller, very creatively, creates an LLDP packet. Piece of software creates a packet like that. And oh, by the way, the controller can send packets to the switches and tell them to forward out ports. So the controller sends an LLDP packet down to the switch. A unique LLDP packet has some unique payload, and it says, you know, send this out port 1. And it waits to hear from any other switch if they receive that packet. And if there's a switch connected to port 1, that other switch will send a note to the controller saying, hey, I just saw this LLDP packet, and here's the packet, and it came in on my port 5. Okay, now the controller knows port 1 of this new switch is connected to port 5 of this existing switch. And the controller can create unique packets for each port on the switch, send them all out, see where they come back, and all of a sudden, the controller now has this kind of real-time updated topology view of how these switches are interconnected. And it's actually not very hard. Okay, so I said most of the stuff we're going to talk today about is OpenFlow 1.0, the hands-on stuff. I'm going to talk about what happened between 1.0 and 1.1. No one is doing 1.1. But the big change took place at 1.1. Now, in 1.0, we had a flow table, and it had fields like header fields, counters, actions, priorities. There's some other things like timers. Starting in 1.1, header fields become match fields. So they actually changed the terminology. They have priorities and counters, but then they have something called instructions. And they also support multiple tables. And in the old way, in 1.0, it was really simple. If a packet matched the thing in the header field, then the action, whatever was in the action field, happened to the packet. Done. You know, if you had stuff that was, and your priorities were used to break ties, you know, if a packet matches more than one table entry. But really simple. Done. In 1.1, it gets more complicated, and you need to think about a new abstraction, and that is sort of this data structure that's moving through the pipeline of the switch. And this data structure has a couple of things with it. It has a blob of metadata, just 32 bits. There are instructions, and I'll talk about this more in a minute, that can set and test those bits. You've got the packet itself that's moving through the pipeline. And then you've got what's called an action set. And an action set is essentially where you can accumulate things you need to do to the packet when you're finished processing the packet. In 1.1, there was a new table introduced called the group table. And a group table, you can have sort of an instruction in the regular flow table entry that says process this using a group table entry. So for example, if you had a lot of packets that were going to a common next hop, they might need common encapsulation and a common forwarding. But you might want to have a whole bunch of different table entries that identify packets going to that next hop. And so if the next hop changes, rather than changing a whole bunch of entries that are identifying all the traffic that goes to the next hop, you just want to change the behavior of that quickly. And so the group table gives you a level of indirection on what you do to a packet that allows you to have that kind of efficiency. Group tables also are where you get features that allow you to do things like balance traffic across bonded links. So again, in 1.0, does the packet match the flow table entry? If so, perform the action. In 1.1 and forward, including 1.2 and 1.3, does the packet match the flow table entry? If so, look at the instructions. We don't have actions anymore, we have instructions. Instructions may be immediate actions that kind of like the actions were in 1.0, but they can also be things that tell it to do something to the packet later on. So the instructions can set things in that action set. Remember, I said there's this new blob, this new data structure moving through the switch, and part of it is collecting things that need to happen to the packet before the packet leaves the switch. And so these instructions can essentially populate things in that data structure, telling it to do things to the packet. For example, push this VLAN ID on it, rewrite the IP address, change disk serve code point, something like that. Collecting things to do to that packet before it's left the switch. So you can start to keep a list of things to do. And this exists because in 1.1 you can have more than one flow table. So you can have a packet come in and match an entry in flow table 0, and the instruction might be, okay, ultimately rewrite the diff serve code point, and then jump to table 3. Packet goes to table 3, and it sees if there's a match there. And in table 3, you might add another action. Okay, rewrite the destination MAC address and output port 2. So you need a way of since you have multiple tables and the packet can be processed by more than one table, you need to have a data structure that's keeping track of what each matching entry in a table wants done before the packet leaves the device. Now, in addition to that, I remember, yeah?
Are the instructions bound to each bit set before, or are they dynamic?
So are the instructions bound to each bit set before dynamic? So the instructions are the controller, using the OpenFlow protocol, creates a flow table entry, and that entry has instructions, and they're fixed. So it's not like it's a Turing machine. So those are fixed, and they won't depend on what's in the packet.
Does bit 4 always mean change MAC address on any switch?
There's a part of the switch that presents this abstraction table, which may be different than the hardware table underneath, and there's some opcode that means do this thing, and it's the same across all switches that support OpenFlow. And then there's some software on that switch that translates that into whatever it needs to be for that particular piece of hardware. And I'm not sure I'm answering your question. Close enough? Okay. You can have, instructions can say to jump to a higher number table. They can't say jump to a lower number table, so you don't have this, you can't have things back up, essentially. The pipeline only moves forward in the switch. And I think I was starting to say, one of the things is, in this data structure that's now moving with the packet through the switch, remember the 32 bits of nothingness at the beginning? An instruction might say, set bit 20, and then in a future table, an instruction might say if bit, or a match might say if bit 20 set, do something. So you can start to not only collect actions that need to take place on the packet in the action set, but you can also flag the packet so it will match specific table entries further down the pipeline. So you can see it got a lot more complicated. Okay, again, 1.1 introduced multiple flow tables, introduced a group table with multiple group table types. Instructions can jump to other tables, but only in a positive direction. OpenFlow quality of service. So in OpenFlow 1.0, there was some really primitive quality of service things. There was an optional action. Remember, an action is doing something like output a packet. There was an optional action which was enqueue. So you could enqueue to a specific specific queue on a port. So outside of OpenFlow, maybe the manufacturer of the switch gives you the ability to define queues, and those queues have different queuing mechanisms, maybe rate limiting or whatever. Within OpenFlow, there's an optional action which lets you, if I match on this packet, the action is enqueue this packet to a particular queue on a port. So you get that functionality, pretty primitive. You can also match on and mess with the header fields, which could include VLAN priority, IP toss bits. So you can do some, you can do some marking, or you can make decisions based on marks, but just on the marks. So it's not particularly useful. We'll jump to OpenFlow 1.3. For quality of service, it has the stuff we just talked about, the primitive stuff from 1.0, but it adds a new table type. So we've gone from, in 1.0, having just the flow table, to now having one or more flow tables, a group table, and now in 1.3, a meter table. The meter table is a lot of QoS rope. Essentially, a meter table has, an entry in a meter table has a meter table identifier, just a number. It has a list of meter bands. That's essentially traffic thresholds and what to do for that threshold, and then it has some counters. So in OpenFlow 1.3, you can have an instruction that says, associate this thing I just matched, the traffic that's hitting my match field, with meter number 3. And maybe in meter number 3, there are 2 meter bands. And the first one is 100 bits per second to 100,000 bits per second to 200,000 bits per second. And the next one is 200,000 bits to 500,000 bits. So all of you might have a bunch of different match fields all pointing to the same meter identifier. So this traffic is being aggregated into one meter identifier, and based on which threshold or band that aggregate traffic hits, different things can be applied to that traffic. And the only things that can be applied to that traffic, at least right now, there are only 2 band types. One is drop the packet, the other is remark the diff-served code point. So if you had a bunch of traffic pointing to one meter table entry, and the aggregate of that traffic never hit the first threshold, it's just going to be processed normally. But if the aggregate of that traffic is enough to hit the first meter band, but not the second, it'll do whatever the first meter band is, and the only kinds of things that can be done are either drop the traffic or remark it. So actually quite a bit of rope here, kind of complicated, but this is the QoS mechanism in 1.3. The key paragraph in the spec, which I copied, the meter applies the meter band with the highest configured rate that is lower than the current measured rate, is a complex way of saying these things are thresholds that you hit. I know we're going through this fast, but we need to. Okay, so we're going to do a couple of hands-on exercises. How many people? Yeah. Okay, so 50 of you have gone to the registration page, and thank you. We fund these events through selling your email addresses, so that's good. So just a quick overview. You know, OpenFlow is actually really simple. It's about this common abstraction of this table. These tables already exist in these devices, but this just normalizes them to a common abstraction. And what's in this table controls how the devices forward packet at wire rate. And we're taking the piece of software that maintained that table and we're moving it outside the device to a central controller. Normally, an OpenFlow device connects to the controller, but as I spoke earlier, usually you can set up an optional port to listen, TCP port that they can listen on, and you can talk OpenFlow to that port, and you can do both at the same time, and that's really good for debugging. Okay, we're going to use something called Mininet. I'm just curious, how many of you have heard of Mininet before? A few, okay. Mininet will create a simulated network environment on the VM that you're going to log into, and it uses Open vSwitch. It's based on Linux containers. It's kind of cool. If you're interested, you can look up all the stuff on the web. We're going to be making very basic use of Mininet. When we run Mininet, it'll create a topology, and then you can do some really simple things like ping things. So our topology will have a couple hosts on it, and if we wanted to ping host 3 from host 2, the syntax looks like this. At the Mininet prompt, you'd say H2, saying I want to run this command on H2, ping space H3. Okay, so I'm gonna zip back in the slides and re-give you guys all the login information because we need you to do this on the VMs. Okay, so what you should have done is once you've got in the registrations, in the roster spreadsheet, you looked at your row number on the left, just what row your name ended up in, and you need to open 2 terminal windows to a VM, and the username is OpenFlow, password is OpenFlow, so typically this would be SSH space OpenFlow at, and it's VM, and then that row number, .training.incenter, spelled weirdly, INCNTRE.org, password OpenFlow, all lowercase, and then you also need to point your web browser to VM, your row number, training.incenter.org, port 8090/guacamole. Now, let me show you what you're going to see when you do that. When you point your browser, you're going to see this login screen, and you're going to type OpenFlow and OpenFlow. By the way, guacamole is like ultra cool. You guys should. You have questions about guacamole? How many of you know about guacamole? Oh, there should be a thing on guacamole here. Basically, it is an HTML5. It turns your desktop into HTML5, dynamic HTML5. So you're going to, when you go to that webpage, you're going to see this Wireshark, but you're probably going to notice that you can't get any of the menu items to work on Wireshark, and that is because there is an error message that is carefully hidden from view that you need to dismiss. Oh crap, where's mine? Is it on the bottom? Lower left? Okay. Okay. Okay, so let me just tell you what you have to do. You're going to have to, and I apologize, this isn't something we can easily solve. Oh, there it is. See that error dialog that's carefully hidden underneath? You have to dismiss that before you can use Wireshark. Okay? So you guys are going to need to do that. Let me go back to my slides. You guys like Google Docs for this? Is this working out pretty? Yeah? Okay. Don't work ahead. Okay, so in one of your terminal windows, you need to do sudo space mn for mininet --mac space --switch space obsk space --controller space remote, and hit a return, and you should get a oh, if you get asked for the password, it's OpenFlow, right? Yeah. If it says what password, just type OpenFlow, lowercase, and you're going to create a topology that's going to look like this. So it's going to create a host 2 and a host 3 and one switch, and this switch is an OpenFlow switch. Now, there's something a little weird about how we have to access this switch, which I'll get to later. But essentially, this switch is trying to connect to your OpenFlow controller, which you're not running. Do not skip ahead, please. So this switch is up and running. It's an OpenFlow switch. It's trying to talk to an OpenFlow controller. So you should have this topology after you run this command. People are okay. Now, I want you to configure your Wireshark. Dismiss that error message in Wireshark, and in the filter field in Wireshark, put OF for OpenFlow, lowercase, and also tell Wireshark to capture on the loopback interface. And so what we're going to do is we're going to watch the OpenFlow protocol between the OpenFlow controller and the switch, and we're going to see how this works. Okay, let's see how much time do I have. We're going to use a tool called OBS OFCTL. This comes with the OBS switch common distribution. This is actually a really useful tool. So if you actually want to play with OpenFlow, this is a command line tool which is going to let you look at the flow table in the switch without going through the controller, and we'll be doing that here, and this is in fact how you would debug something. So we're setting up a situation here where we're putting Wireshark along the channel between the controller and the switch, so we can look at the OpenFlow conversation between the controller and the switch, and we're also going to use OBS OFCTL to look directly at the switch. So if you had an application that just wasn't working, you could see what the controller was saying to the switch, and then you could look in the switch and see what the switch is really doing in terms of what its flow table looks like. Okay, so in one of your windows, in the other window, the one that wasn't the MiniNet one, you should run sudo space obs-ofctl show dp0. You're doing show dp0 because we needed to do this with a named device. Normally, you would the dp0 would be replaced with the IP address of the switch you were connecting to. So this is, this will tell you that there's actually a port listening on the switch you're trying to look at directly. It'll show you some basic stuff about the switch. Now type super user do obs-ofctl dump flows dp0,
And what you'll see are, there's this flow table in the switch, and dump flows will show you what that table looks like in the switch. And there should be virtually nothing there, hopefully. I'm going to skip ahead just a bit. Okay. So, in your Mininet window, I'm sorry, but I'm running out of time. In the Mininet window, I want you to try to do a ping. So H2 space ping H3. And what happens? Doesn't work, right? Key thing, doesn't work. OpenFlow switches don't do anything until you tell them to, right? It's not like an Ethernet switch where you just have connectivity by connecting to it. It doesn't work that way. So this switch periodically is trying to connect to a controller, but you're not running a controller. So let's start a controller. The super user do OBS-controller, PTCP, and you can put in the background if you want. That starts up a really basic controller that comes with the OBS distribution. And if you don't tell that controller anything else, it will try to make the switch behave like a regular Ethernet learning switch. So type that, and then go back to your Mininet window and tell me, do the pings work now?
What slide is that?
Thank you, sorry. We were never going to get here if I went through them. So when you did the pings before you ran the controller, they'll just fail. Hopefully, once you run the controller, the pings will work. Now, this is where it gets really kind of interesting. Your Wireshark window should have just filled up with OpenFlow salad at this point. So you are now running a learning switch. So we took this switch that didn't do anything, and we thought, oh, there's this feature, learning switch, kind of a basic feature. Actually, it turns out to be one of the harder things to do. And we've moved it out of the switch. We've moved it into a controller, and you're seeing it operate right now. Now, do those pings every now and then, and run this command again. Again, this is the command you would run if you were debugging something, and this command talks directly to the switch, and it says, show me the flows, show me the flows. So you do the pings and run this, and now you're going to see those flow table entries that the controller is putting in the switch to make that switch behave as a learning switch. And it's going to be pretty dynamic. You run this a couple times, it's going to look different maybe every time. Okay, so we've got 13 minutes left. Here's what I'd like to do, because there's one other thing I want to talk about, and I want to save a little bit of time for this. You can do this exercise at home. All you have to do, and everyone who put their name and real email address in the roster, we will send a pointer to where the Amazon machine image is, the public one we made that has these tools, and some cryptic instructions for how to spin this up under your own AWS account, which should be for free. I can't promise that, but when you get a new AWS account, you get so many hours of the micro instance, and I think this will run on the micro instance. What you should do, if you want to see what's going on, is look at the Wireshark output, open up all the tabs, and follow what's going on for just a learning switch. Because that will really give you a sense of how this works. And we were going to do that on the screen, but there's not enough time to do that. So I would really encourage you to do this. It's not rocket science, but it's pretty interesting to watch what's happening. This is what I call a reactive application. So traffic comes in. If it doesn't match a flow table entry, it gets punted to the controller updates the switch. A lot of traffic going to the controller. This is useful simple way to do a learning switch.
This might work in a data center or a campus environment, would not work in a WAN. So go ahead in the window you were running the controller and hit Control C. If you backgrounded it, hit a foreground and hit Control C and kill that controller. I'm going to talk through exercise 2. We're not going to really do it. In exercise 2, so in this case, we had a controller running, and we had the controller emulate a learning switch. In exercise 2, we have you manually put in some of those flow table entries. So we don't run a controller. We use this command line utility that talks directly to the switch, normally used for debugging, and we have you put in some really simple rules that turn a couple ports on that switch into repeater ports. Packet comes in one port, they go out the other port. We have you put in rules that are based on ports, and then we have you put in rules that are based on the IP address, and we ask you to give the IP address ones higher priority, and that is so that you can see how the counters change and how priority is used to determine when a packet matches more than one rule, how priority is used to determine which action is selected. And you guys can do this on your own. There's also something we didn't even try to include, and that is using something called FlowVisor to virtualize all this stuff. There's a way to put a device between the controller and the switches. It speaks OpenFlow in both directions. It's essentially a proxy in both directions. It's called a FlowVisor. And it has a set of rules that you set. And the result is you can virtualize access to an OpenFlow environment. But I can't do that in this much time. So you can do these on your own. Because I want to talk to you about one last thing. Is anybody from Juniper? So I cannot remember who at Juniper, but there's somebody who is or was at Juniper who described a term floor plan entropy, which I thought was a really cool term. Maybe. In a multi-tenant data center, in a big multi-tenant data center, you've got this problem that you have. Let's say you have a 1 million VM data center, and maybe you have customer A, and they need 2 racks worth of servers to run their application, and so most of the data is staying in those 2 racks. But these are dynamic services, so maybe on Tuesday they only really need a rack and a quarter, so they deallocate a bunch of stuff, and customer B comes in and takes that second rack and maybe some more, and then customer A comes back and says, well, no, I need to ramp back up, but now what's free is across the data center. And so you have this disfragmentation problem in a multi-tenant data center. So I don't know exactly how Amazon solves this, for example, but you know they have to deal with it. So over time, if you've got these tenants growing and shrinking their resource requirements, either Amazon is going to set up a huge extra amount of resources, or they're going to migrate things around in real time to try to balance things out, which they may do both. But the other problem is fundamentally they're going to have to support high bisection bandwidth throughout the entire data center, because you just don't know where things are going to be. It's opaque. You can't predict what these tenants are going to do. So, that can be an expensive and complicated problem to solve. And if you want to solve it with layer 2 devices and building fat tree networks based on inexpensive devices, that's cool, that will work, except if you have a 1 million VM data center, you can't, or it's too expensive to buy layer 2 devices that will support 1 million CAM entries. And when I say million, I'm not making that up. I mean, a 1 million VM data center is kind of in the order of magnitude that you can expect
in large data centers now, really large ones. So there's a simple layer 2 way to solve this, but then you get into hardware that's expensive and power hungry and awkward and all those things. Here's how fundamentally differently you can approach something if you have OpenFlow. There's a protocol called Portland, and there's a link to Portland in here. And what I'm going to describe is not exactly Portland, because that would take too long, but it'll give you a sense of how you can use OpenFlow to completely change the way Ethernet behaves to solve a real problem. So let's say we were going to mess with the Ethernet address, just the destination Ethernet address. And in this data center, when a VM ARPed to talk to another VM, that we had an ARP server, and that ARP server would give it kind of a fake Ethernet address. And that fake Ethernet address would have some structure to it. And maybe the first 2 bits in that Ethernet address get left alone, but maybe a few bits are used to describe, from a topology perspective, what corner of the data center that destination is in. And maybe a few more bits describe what row. You know, if it's in the northwest corner, what row. And maybe another one says which rack, and another one says which server in the rack, and then you got some bits that say which VM it really belongs to. Now, you can have switches that are configured in a fat tree network interconnecting this entire data center, and their rules are tiny, right? It's like routing. So you've highly aggregated these rules because you've flipped Ethernet on its head. You said, no, the destination address is not some unique thing bound to the VM with no other meaning. They're actually getting destination Ethernet addresses from the ARP server that provide a route to get to that VM. And so the switches that are interconnecting all this can have a really small table. Now, when the packet gets right next to the VM it's heading to, you've got to do one other thing. You've got to rewrite that MAC address to be the MAC address it's expecting. Now, what's cool is if your VM environment is using something like OpenVSwitch, you can write those rules with OpenFlow. And if the physical switches in the room support OpenFlow, you can have orchestration software, networking software, an ARP server that's set up to do this, and it's not that complicated. And it gives you a way to solve a problem in a completely different way. You know, it's like, I don't know if you guys read, and I don't know all the details, Google recently solved the, you know, you can't have a widely distributed database that is fully consistent all the time and fast. Those things cannot be all, you know, it's what, good, cheap, and fast or something. You can't have all those. And Google said, well, actually you can. We'll introduce a common clock, precise clock into all this, and we have a scheme that lets you break the rules. Well, OpenFlow is a way to really change the way you think about forwarding packets. And fundamentally what it means is all those fields that had fixed meaning at the beginning of the packet, you can use however you want to use them. And in VM environments where you have, as the last hop and the first hop, vSwitches, you can fix the packets back up so there's no in-system changes. The VM software doesn't change. You just put the packet back in some form it wants to see it in right before it gets there. So I am out of time. Questions? You guys can send me email if you, yeah. So in OpenFlow 1.2, so in OpenFlow 1.1, they changed the way they encode the header fields or match fields to be type TLD, type length. Thank you. Type length value. In 1.1, they made that change, so it would be easier to incorporate things like
v6. In 1.2, they support v6. So the question is, well, then what do vendors supply? And I should probably say a few words about this. A bunch of vendors did 1.0 because 1.0 was simple enough that they could update their firmware and get their existing devices to do it. My understanding is most vendors are talking about serious products designed for OpenFlow to support 1.2 or 1.3. Nobody's doing 1.1. And they're focusing on 1.2 and 1.3. The other problem, so the lab where I work does, it's an interoperability lab and also a conformance lab. And the OpenFlow spec is unfortunately a bit vague in terms of what's required and what's optional. And today, if you go out and buy a switch, one of the things to understand is what the vendor actually, so a vendor might say, yeah, I do OpenFlow, and you have to say what parts of OpenFlow and what are the limitations. You know, can I do layer 3 and layer 2 matching at the same time? Can I, you know, what's the table size limit? How many table entries per second can I update? You know, that's all brand new and scary space because most of the products out there, you know, they weren't built for this. They were adapted to it. Soon we're going to see stuff built for it.
Real quick, can you give an overview of the open source ecosystem on the controller side?
So the open source ecosystem on the controller side, some. So the first controller was something called Nox. It came from Stanford. Nox was a Python and C Franken thing. And that effort has, I believe, forked into a newer Nox, which is mostly C, and Pox, which is all Python. There's also a Java implementation called Beacon, which was forked, and then Big Switch developed into Floodlight, which is still open source. I'm not sure if their commercial product is just add-ons to it or how that works, but and then there's a framework for building controllers called Trema that comes from folks in Japan, and there are, I think, on the order of 10 open source controllers, and I didn't name them all. There are a lot out there. And then there are big companies, both the incumbents building their own controllers and software companies just building controllers. That's probably not a good answer, but anything else? Thank you for coming. Hopefully the people did the hands-on, it worked. And we will send you some email that says how you can get to the image if you want to follow up on this and enjoy your NANOG.
At the end of the slides, there is a couple links to the images, and we'll send out a note with a more complete description of exactly how to spin it up in AWS or in your own VM that you can run on your laptop.